So we ended last time with this proof where we showed that below any CE set there's a simple set, and this was an example of permitting. And so now we'll look at general permitting, and the idea kind of is, okay, so you want to make CE sets A and C that are in this kind of relation for some Turing machine. And so you're going along, and imagine you have your Turing machine fixed already, right? You're going to do some fixed construction, and this has to happen. That A is computable from C, and so if you have some value of A already determined, then at some point enough of C is determined to have that this particular location this computation happens. Let's say X is not yet in A, and you're going along, and so you know that this functional computes A when it has oracle C, so it has to become equal to this. That means that unless you do anything, at some point enough of C needs to be determined that this computes and outputs 0. But now you're going along and you decide that, well, yeah, it happened like this, but I would really like to put X into A. Right? This is what you do in constructing a CE set. You're going along, and every now and then you decide, okay, let's take this into A. But now you can't anymore, because if you now put X into A, then you break the computation. And so the whole point of permitting is that, okay, yes, you would break the computation. When, however, do you not break the computation? Well, you do not break the computation if the oracle changes as well. Right? If the oracle changes as well, then it's okay. So this is the inspiration for the standard permitting theorem. It says that if we have an F which is computable, we have A with a sigma 1 approximation AS, we have C with a sigma 1 approximation CS, and we have that whenever A changes, remember the double restriction was the restriction up to and including X, and because we're most likely to get everything correct up to plus or minus 1, it doesn't really matter that much. This way at least you can give yourself the illusion that you get it exactly right. So whenever A changes, this should be allowed by a C change. This means that there should be a y less than or equal to f of x, where y is in cs plus 1 minus cs. Right? So what is f? F tells you, f of x tells you for x changes, all x changes are allowed below f of x. This is how far you have to look. In the construction we did on Friday, f of x was the identity function. Right? Whenever there was a change in A, there was a similar change in C. Here you can generally allow any function f. Anyway, so this is the input for the theorem. If you have an f and sigma 1 approximations that do this, then it is the case that the A really Turing reduces to C. Right? right? And how do you see this? Well, this is very easy to see. You want to, using C, you want to be able to compute A. Well, how can you compute A if you have a sigma 1 approximation for it? Well, it's enough to be able to compute the modulus of this particular sigma 1 approximation. And you can, because under all these assumptions, the modulus of A at x, right, the time when it first stabilizes, when A up to and including x has achieved its final permanent value, this is less than or equal to the modulus of C at f of x. Right? If there is a change less than or equal to x in A, then according to our implication here, this needs to be followed by a change less than or equal to f of x in C. And if you look at this expression here, you notice this is C computable, right? We have a sigma 1, both of them are CE sets with sigma 1 approximations, so from the set itself you can decide when it has stabilized. Right? If it's just a delta 2 approximation, it's not good enough because it could go back and forth. But because there are sigma 1 approximations, once the approximation is correct on some initial segment, it stays correct on that initial segment. Right? That's why CE sets are better than delta 2 sets. So this says, this value, which you can compute if you have C as an oracle, is an upper bound for this value, which allows you to compute A, and therefore C allows you to compute A. And this is exactly the argument as we did it on Friday. So it says, everybody happy with it? Right? It says standard. Now you might expect a non-standard permitting theorem, but it's really called sort of a general permitting theorem. And the general permitting theorem just follows by some fairly easy observations from this. Right? The proof of this statement is A is Turing computable from C because the modulus of A is bounded by a C computable function. Why is this C computable? Well, because f of x is outright computable, and m of c, the modulus of c, is C computable because you have a sigma 1 approximation. So we can just say, okay, well, why the big restriction on f? We don't need f to be computable. It is enough for f to be C computable, because if f is C computable, then this is still a C computable bound on the modulus of A, and the argument goes through in the same way. You can compute membership in A because you just find an upper bound. So why does this matter? Well, because it matters because what you can do to generalize, I'm not going to write down the whole thing, but instead of having a function f, you can have a function f hat xs. This function is computable. And at any point in time, you have this same permission mechanism, but now the bound is fxs, right? The current bound we're looking at. But we use the idea of standard permitting for f. That is, okay, so at this point in time, you compute f to be this value. As soon as c changes, you are allowed to change this value. Right? And so that's exactly how you generalize from standard permitting to generalized permitting theorem. Whenever this sort of change happens, which is then permitted by C, at those particular points in time, you also allow the value of f to change. Right? So as you're going along, then you can say, now I look to C up to this point. Oh, it's changed. Now in the future, I'm going to look much further out to see if there are C changes. And in the future, I'm going to look much further out if there are any C changes. Now, of course, you're out of luck, or your method doesn't work if this doesn't give rise to a function. So you do want the limit of s of f hat x s should exist. Right? As you're going along in the construction, you can change which part, up to how far you're looking in C, to see if you have a permission to change A, but you can only do that finitely many times. Right? That's essentially what this says. Yeah. Because if you keep looking out further, then you have more changes for C to go, and it changes again, and you look more changes for C, and it changes again. You could shoot off to infinity, and then this doesn't become a computable, C-computable kind of thing, right? You need a definite value there. So that's general permitting. And now you could say, okay, well, looking at this, yeah, very nice. Everybody happy, by the way, with general permitting? Right? You're essentially using permitting on the function f, while using the function f to do permitting, to compute your permitting for the set A. Now the perfectly reasonable question is, of course, okay, so we've found some extra flexibility in the function f. How much better can we do this, right? And that's exactly what the next theorem is about. And the next theorem says this is as good as it gets. Why does it say this? Because now it's the next theorem, called reverse permitting, says that, well, if we are in fact in the context of CE sets, then any Turing reduction can be looked at as an instance of general permitting. Right? So any Turing reduction, maybe you didn't build it through a general permitting. Maybe the construction it is a result of is not even best looked at as an example of general permitting, but it could be looked at as general permitting. In particular, if you're trying to do a construction on CE sets through generalized permitting, and you fail, then the reason you fail might be a very good indication why you are unable to do it at all. It's not that you haven't come up with the right strategy, but you're trying to prove something which is false or something like that. Anyway, so what does it say? It says, if A and C are CE sets with A Turing reducible to C, then there are AS, CS, sigma 1 approximations, where AS is a sigma 1 approximation of A, CS is a sigma 1 approximation of C, and F hat of XS computable that satisfy general permitting. It's certainly not the case that every approximation to A and every approximation to C would have this nice relationship, but they can be chosen. There exist such approximations that have this nice property. Right? The nice property being that whenever AS changes on an initial segment, it is because CS changes on an initial segment as indicated by the current value of F, and F only changes its value, right, as S increases, it only changes its value when C changes its value on the initial segment determined by it. So this says exactly that all Turing reductions could be looked at as an instance of general permitting. And it's kind of nice because the proof is somewhat reminiscent of what I started with here. Look at the Turing reduction like that, see what happens to it. So what we have is that we know that they're Turing reducible to each other. So there exists such an E, such that using the oracle C, you compute the characteristic function of A from it. We also know these are CE sets, so they have sigma 1 approximations. So let's write them A hat T and C hat T. Right? These are arbitrary sigma 1 approximations for A and C. We know they exist because they're CE sets. It would be a very big coincidence if these were the right approximations, but we don't care. So what we're going to do is we're going to take these sigma 1 approximations and change them around a little bit until we get the right sigma 1 approximations. And so what is the idea? Well, for any given part of A, if it were correct, then you can find a sufficiently far enough along approximation such that this reduction works for these two. Right? Now, of course, we don't know what A is because A is CE. It might be very complicated. So you can never know when you have a correct approximation to A. But for any approximation which you momentarily presume to be correct, you can look far enough ahead so that C computes it using this reduction. And that's what this is based on. If I look at G sub S, S is a stage in time, as S. Right? S is a stage in time, and what we're looking at, we're looking from S into the future for a time which looks good to us. So G is short for good. We're looking for the least time t which is greater than S, such that for every x less than or equal to S, so we're looking at an initial segment of A determined of length S, or S plus 1. And what we want is, for this fixed initial segment, at some point the A approximation would be correct, and then at some point later, using the C approximation for that part of the A approximation would be correct. Now we never know when we actually have the correct values, but we do know that if we just start looking into the future, at some point these two things will line up. That is to say, at some point it will be the case that for all these things, phi e of C hat x as computed up to time t, right? This functional is allowed to take t steps, and we use the t approximation of C. This should converge and be equal to A hat also as computed at time t. So this function is doing exactly what I was describing before. Start looking at time t, start looking into the future until such time when the approximation of A corresponds to the approximation you can compute from the approximation of C. Doesn't mean that either value is correct, but it is a time when they are in sync. Right? And now if we look back again at our original idea of how permitting worked, we notice that, okay, so whenever they're in sync, if they're not correct, if I want to change A, the only way to change A is if C changes and allows it. So this is exactly what we now choose to do. We say AS, yes, the approximation at the next good state in time, and CS is the approximation also at the next good state in time. And then I just need one more thing, which is the function f, which tells me how far I have to look. Well, how far do I have to look? I have this functional here which uses part of c, and that's exactly the part where the change has to happen. So I can choose my function f. F hat of xs is the supremum of z less than or equal to x of the use of e of c hat z t. I have here a case distinction which or 0. So this is otherwise. Why do we need this? Well, because if we're looking for the use of x, as long as x is larger than s, then it doesn't make sense to talk about the use. So you can put this distinction in here, as long as x is greater or equal to s. Less than or equal to s. Right? But I guess the only point being here is that we really only care about the limit value of this function f, right? So this is what happens. But if you don't put in this distinction, then this function might accidentally be defined a couple of times and accidentally change a couple of times without corresponding c change, which is why we want to have this limit in there, so that these uses are really involved in these computations over here. Everybody happy with that?
Is that t in the use function? That's meant to be g of s, is that right?
That would be s.
It's s, okay. No, you're looking for the highest.
No, I want when this happens. Yeah, that should be g of s. Exactly the uses as we use them to determine these things, which is exactly the use of these functions at time g of s. Exactly. Yeah, so this should be g of s. So you start with arbitrary sigma 1 approximations, and then because you know the Turing reduction is a reduction, you know every now and then they are in sync, even though maybe you have the wrong values at that time, but you can look for when they are in sync and take that time. And that was exactly our original idea for permitting. But only changes happen when the use changes, because these things have to stay in sync along the way. So that's kind of nice. Okay. So this was just a nice analysis of a method in between. But the path we were really on was sort of, I guess, following in Post's footsteps, where first we defined creative sets, and we noticed they didn't quite do the job they were supposed to. And what was the point of creative sets? Well, they are such that their complement cannot be described as a CE set in some effective way, right? Whenever you had a CE set contained in the complement, from the index you could compute something which showed a difference between that CE set and the complement of the set. And the complement was productive. Then we went on to simple sets, where the idea of simple sets was, okay, now we're gonna sort of maybe more strongly describe the complement as not being a CE set, because the complement does not contain an infinite CE set. Those were our simple sets. And so what is a CE set? Well, a CE set is like this enumerated set, right? And an infinite CE set can be enumerated injectively, where you have one number after another. And so what it says to be simple is that whenever you have an enumeration, an injective enumeration of infinitely many things, and you're trying to keep guessing it into the complement, you keep failing, because there is no infinite CE set in the complement. So whenever you try guessing like this, you keep failing at sticking all of them in the complement, and this was supposed to mean that the complement is very thin, right? It's such a small complement that it doesn't even contain an infinite CE set. Where creative sets have all of their complements have this infinite set in there. So now we're going to increase it, or increase our strength of guessing a little bit. Instead of just going along and guessing one element, we're going to strengthen this notion and say, okay, the guesser gets more power. Instead of guessing one element at a time, he gets to guess finite sets at a time. And these finite sets don't need to be completely contained, but they need to at least hit the complement. Right? This is giving our opponent more power. He cannot just, he doesn't single out elements, he just says, here's a finite set, and one of these elements does it. I don't know which one, but that's up to you. So that's a stronger notion, and we'll see what we get from that. So we say Fn, n in omega, a sequence of finite sets is a array if and only if there is a computable function f such that Fn is equal to the finite set determined by Fn. And I realized that okay, of course these finite sets were interesting, because if you're not trying to do anything effective, a finite set is a finite set is a finite set, there's not much interesting going on. But if you're thinking about it effectively, we notice that describing finite sets in different ways is effectively really different. If I give you a CE set where the guarantee is finite, you still cannot compute the maximum element from this set. And so that gives us two options for these arrays. There are strong arrays where the function Fn gives you, what was it called, the characteristic index or something like that? The canonical index, yes, the canonical index. So here you have the complete set in your hands. The binary expansion of Fn gives you exactly which the elements are in there, and from that you can see what the maximum element is and things. It is a weak array if we have the guarantee that these sets are finite, but all you're given for them is a sigma 1 index, which gives you effectively a lot less information. So these are going to be the guessing objects we use for the functions. We call such an array disjoint if each of the finite sets are pairwise disjoint, right? The only thing you have, because otherwise you could cheat by figuring out one element of the complement, and each of your finite set contains that one element. Well, yes, then every of your guesses includes a correct guess, but you still didn't guess anything. So you want pairwise disjoint things, kind of corresponds to the injectiveness of the function in the CE case. Then we call a set hyper immune if no disjoint strong array has F intersect B non-empty for all n. Fn. A set B is called hyperimmune if there is no disjoint array such that in every one of the finite sets you guess one of the elements of B, the other ones might be completely outside of B. B is its terminology is of course very tacky or whatever, but the next one, B is hyper immune. I apologize ahead of time. B is hyperimmune if there is no disjoint weak array that satisfies this. And that's a stronger thing, because any strong array is a weak array, but from weak arrays you can't always find the strong arrays. Hyperimmune.
That's super duper.
Exactly, yes, super duper. And then of course, right, just as simple meant its complement is immune, hyper simple means its complement is hyperimmune, hyper simple means the complement is hyperimmune, we write usually H simple or H8 simple because I guess I'm not the only one slightly embarrassed by the terminology. It's not mine. That's not mine. It's voices of me. It's well known. Been like that for a while. Okay. G is computably bounded. If and only if there exists an F which is computable such that for every x, G of x is equal to the F of x, right? Which is to say, G is computably bounded if G is computably bounded. If we have a set of natural numbers, then to this we can associate the increasing enumeration function. I guess I want this one to be infinite. Otherwise, the function is partial. Where PA of x is the xth number in A. But, PA of 0 is the smallest number in A. PA of 1 is the next smallest number in A. PA of 2 is the next smallest number in A. We say A is computably bounded exactly when P of A is computably bounded. These are definitions where, except for P of A, right? Why would you call it P? But the other definitions, if you didn't already know them and I used computably bounded, then you should have guessed them. Very reasonable kind of definitions to make. Why did I do that? Well, hyperimmune and hyperimmune are sort of good generalizations to say that simple complement is very thin. These complements are even thinner. Even with more guessing power, you still can't do it. And so these definitions are here because of the following theorem. We know nice, interesting things happen with simple sets, and so here we get some nice characterization for hyperimmune. An infinite set A is hyperimmune if and only if A is not computably bounded. which is kind of a nice characterization of the one way it gives a nice characterization of hyperimmunity, the other way it gives a nice characterization of not computably bounded. I think they're right? Both notions are kind of nice, and they happen to be exactly the same. Okay, good. How does this work? Well, it works pretty nicely. Essentially, in some sense, there's just some simple observations involved. The definitions look very different, but they turn out to be fairly closely related. So, the one direction, suppose A is not hyperimmune. Well, what does it mean not to be hyperimmune? It means that we have such a strong array, which in every of the finite sets there is one element from our set A. Right? So you look at the first finite set, it contains an element of A. So in particular, if you look at any number bigger than all the elements in the finite set, then you have an upper bound for the first element in A. If you look at the first two finite sets, then while they are disjoint, each one of them contains an element of A. So if you look at an upper bound for all the elements in these two finite sets, then you have an upper bound for the first two elements of A. And why can you do this? Because we are dealing with hyperimmune, which means that we have the canonical indices of the finite sets, so we don't have to search for the elements, we have them available to us. And so really, what I'm saying is that this function, f of x equal to the maximum union of the d of g y, where y is less than or equal to x. Right, the function g is the computable function which gives the strong array, and then from this you can compute the maximum. So this is something which is computable, and what do I know? Right? Maybe +1 to be on the safe side. I guess I don't need it, right? It says less than or equal here, so I don't need the +1, but it doesn't hurt me either. And this clearly does it. So that leaves the other implication, and in some sense based on a similar idea. So we have that PA is less than F. This is computable, right? We have a computable bound. This is not less than or equal star. It is less than everywhere. It makes a difference because in the guessing here it really says for all n you have to guess, not for all but finitely many. But it doesn't really matter, because if you have it for all but finitely many, then you can change things around a little bit to get it for all but finitely many. Now, what did I say? If you have it for all but finitely many, you can modify it a little bit to get it for all. At the very least, you can take a strong array which has this non-empty intersection for all but finitely many, and just start your new array by cutting off the initial segment containing all the exceptions, and then you have a strong array that works everywhere. So I guess This matters because we chose the definitions the way we are. It's not a deep fundamental observation. And then we say G of G naught, that's rather obvious. Gas, we know that F naught is greater or equal to P of A naught, so the first element of A is less than or equal to F naught. And now you look at this and you see, just generalize. How do you generalize? Well, there's one more observation you need, and that is that PA of K, the kth element of A, enumerated in increasing order, is clearly greater or equal to K. So that tells me that if I choose Gn plus 1 to be the set from K to F of K, where I have to choose K to be the right kind of thing. K is 1 plus the maximum of the union of all the earlier computed ones. And then why does this work? Well, it works because K is less than or equal to PA of K, which is less than or equal to F of K. And now I realize that K is a little bit more complicated than it needs to be. Of course, this is another instance where I looked at the proof in the book, decided what the key idea was, agreed with what was written, and it's correct. But these are all sequential increasing intervals. So this is the same as the right endpoint of the previous interval plus 1, which is a slightly simpler expression than the one written here. Although I guess I did not introduce the notation for the right endpoint of the previous interval, but it's the same anyway. So nice characterization of hyperimmune.